I think it's no. Maybe this one. Yes. Okay. You hear me? That's a bit low. Okay. Today, in the afternoon session, I will give two lectures. First one is on particle physics, and then the second one is on accelerator physics. I will give a break after the particle physics lecture, and then we will continue for the second lecture. Let me overview of my talk first. We start with the units in the particle physics and historical introduction to the elementary particle physics, and then forces in nature, symmetries, and hadrons, which we group particles in according to some group theory, and particle decays, interaction cross sections, and the standard model, and why we go to the beyond it. I will shortly mention about this case. I want to pass very quickly some of the slides, because you are already known, most of them, but some of them is so important. Then, for example, we use in particle physics the natural units. Natural units, what I mean by natural units, the h bar is the unit of action, Planck constant over 2 pi, speed of light c, they are all equal to 1. In this case, the unit of energy is given in GeV, mass is also given in GeV, and momentum is also given in GeV. For this reason, let's calculate the proton rest mass energy here, 938 MeV. If we take C is equal to 1, then we have the mass unit in the energy unit. We use these units all in all the lectures. Second, we have the time, length, and area units. Time and length is also given in inverse GeV here, if we take h bar and c is equal to 1. But the area is given in inverse GeV squared. Okay, if you go back to the SI units, then we want to we can translate the natural units to SI units, multiplying relevant factors for the h bar and c. In the Heaviside Lorentz units, we set also h bar c and epsilon 0 and the mu 0 is equal to 1. Then the Coulomb's law becomes in this form, in this unit. The electric charge has the dimensions, this FL square over 1 over 2, and h bar c over a half. Okay, let me start with the historical introduction, because long time ago people have asked what is the world made of, and what holds it together, and another question, why do so many things in this world share the same characteristics? There are some categorization or classification that Empedocles says the universe is made of four elements, four things: air, fire, earth, and water. In 400 BC. Then people have come to realize that the matter of the world is made of some few fundamental building blocks, which we call them today elementary particles. Democritus in 400 BC says in reality there are atoms and space. This is another view for the structure. Okay. Yeah. Sorry. Back. This one. let me continue and then discuss maybe in the coffee break later on, right? Okay, Mendeleev categorized atoms into groups that share this, similar chemical properties, but later Mozole's work showed that the modern periodic table is based on the atomic numbers of the elements rather than atomic mass. On the experiment also helped scientists determine the atom's structure, and it consists of a nucleus and the electron cloud. So particle physics starts with the with an experiment, Thomson experiment, because the electron was discovered in 1897. In this experiment, it's called corpuscles for the electron, but electrochemists in an electrochemistry experiment, electron word is used by Stoney. Okay, there is also another experiment which is important for the particle physics. It is Rutherford experiment. In 1909, Rutherford set up an experiment to test the validity of the theory. Here, sending alpha particles to the target, then expect the target is gold here, and alpha particles. The expectation was that alpha particles go into the gold and then makes some expected marks on the screen here, not on the backwards and other sides. But the experimental result was that here you also see another marks on the screen, even at the backwards. So this shows that gold plate is made of atoms, and then atoms are not very close to each other. Then there may be some gap between them. Some of them scatters, some of the alpha particles scatters at large angle, and some of them will not scatter. Then we will get this pattern. So it means that an atom has a nucleus inside it. So the nucleus was a positive charge. Okay. After these two important experiments, I will shortly mention on other discoveries and important events. Photon in 19, so Planck explains blackbody radiation and says radiation is quantized. Einstein proposes a quantum of light which behaves like a particle, photoelectric effect, equivalence of mass and energy, and special relativity. Later, Compton found that light scatter from a particle at rest is shifted according to the according to this law. It should be lambda, but fonts are not good to explain everything here. Lambda prime is equal to lambda plus lambda c Compton wavelength 1 minus cosine theta. This one can be read in this way. Okay. The name photon is suggested by the chemist Lewis in 1926. Okay. Another event for mesons. Mesons are discovered in the years 1930s because meson means middleweight, baryon means heavyweight, and leptons lightweight. They are used commonly. And Yukawa theory for strong force suggests that a particle which has a mass around 300 times the electron mass. Okay, in 1930s to 50s, Dirac equation gives positive and negative energy solutions, and this can be the good solution for particle antiparticle, and there is a Feynman-Stuhlberg formulation in 1940. Anderson discovers positron, and antiproton and antineutron was discovered at Berkeley in 50s. So the important another important thing is the nuclear beta decay. Pauli suggests neutral particle to explain the continuous electron spectrum here. Chadwick discovers neutron in 1931, and the Yukawa meson theory of nuclear forces in 1934. The discovery of the strange particles lies in 1947 to 1960s. And then strange particles, for example, K meson, it is discovered in 1949 via its decay. Neutral pion is discovered in this year, and the discovery of particles called delta baryon, which are spin 3½ particles, higher excitation. Young and Mills developed a new class of theory called the gauge theories in 1954. There is also unification and classification ideas in the years 1950s. So Schwinger makes this, and another ideas, Gell-Mann, Zweig, mesons and baryons are composed of quarks. It's a suggestion. And omega particles discovered in this year. Greenberg, Han, and Nambu introduced quark property of color charge in 1965. And the electroweak theory, Weinberg and Salam proposed a theory that unifies electromagnetic interaction and the weak interaction. Later, electroweak theory in the 70s, Glashow, Iliopoulos, and Mayani they suggest 4 type of quark in the context of standard model, and the Z boson has no flavor changing weak interactions. Later, Friis and Gell-Mann suggested the strong interaction theory, QCD, quantum chromodynamics, in 1973. Pulitzer, Gross, Wilczek discovered the color theory of strong interaction, which has a special property. Now we call it asymptotic freedom. At well higher energies, partons behave as if they are free. In 1974, Iliopoulos presents the wave of particle called standard model. So there is also new members in the story because fourth quark, the C quark, charm quark, is discovered in these years, and the D0 meson is found in 76. Tau lepton is found at slag 76, and the Lederman at Fermilab discovered the bottom quark in the experiment, and this leads to the search for the sixth quark. It's top because of the symmetry. And the standard model in 1978, because in 1983 W and Z boson discovered, observed at CERN by Rubia team, and in 1995 CDF and D0 experiments at Fermilab discovered the top quark, which has a mass around 175 GeV. Okay, let me summarize the timeline shortly here. It starts with the electron discovery here in these years, and then very important events in the timeline, and then we come here, the discovery of the top quark in 1995. Okay. Later, after these years, there will be some discovery also. We are expecting from the LHC to discover maybe first Higgs and then some exotic particles. Okay. In particle physics, we deal with high energy because small particles, smallest particles, and the fastest particles are the ingredient of the particle physics. Because at the very small scale, particles obey some physics rule, and we call them quantum field theory. Quantum field theory here, maybe we can make a comment on when we go to higher speed in this direction, and we can go to smaller sizes in this direction, then the validity of the mechanics are shown in this plot. Okay, on the other side, there is also experimental information that comes from the from three main sources. For example, from scattering events, scattering of the particles, collision events, and decay events, and also the bound states of them. Okay, in particle physics, we're curious about the structure of the matter, and also we use the tools for the research. What we use, for example, if we look into the bacteria at 10 micrometer, this is the scale. If you want to look at the virus, for example, this is 100 nanometer, and atoms in DNA, which is 1 nanometer. These are all the small scales, but in order to reach the small scales and the higher energies, we need particle accelerators at high energies. Energy and the wavelength is inverse proportional because due to this formula, if we have higher beam energy at accelerators, for example, then we will have shorter wavelength according to this formula, and we will get the better resolution, what we are searching for. The Rutherford experiment showed this idea, and we know the nucleus inside the atom. So the particle physics is the study of the matter and the forces. Matter means spin 1/2 particles, and these are the fundamental constituents of the universe. We call them the elementary particles. Force means spin 1 particles, the fundamental forces of the nature. There are some particles carrying the forces which have spin 1. I will mention about them in the later slides. We know the atoms here in this some times ago, 90 or 100 years ago, and 60 years ago we know nucleus. 40 years ago we know proton, neutron, and electron, and the present today we know still up quark and down quark as the building blocks of the matter. So what comes later, we don't know. Maybe if quarks have a structure, then there will be some picture here. We may call them prequarks, like that. Okay, let me go another slide. If you group matter and forces in the particle physics, ingredients are for the matter quarks and leptons, because they are fundamental at this level, at this energy scales. Okay, and then quarks combine to form hadrons. Hadrons means mesons and baryons. Baryons can combine in nuclei, and the atoms and the molecules. If we go this way, then we will have composite particles. They are all composite particles. Quarks and leptons at this level, not composite, they are elementary. We will have 4 force carriers here: gluons for the strong interaction, W and Z bosons for weak interaction, photons for electromagnetic interaction, and the graviton for the gravity. In this panel, you see the strong interaction and the weak interaction and the electromagnetic interaction. 3 of them can be combined in a unified theory, which is grand unified theory, shortly called GOT. And the electroweak theory combines 2 of the interactions, weak and electromagnetism here, and the gravity remain different here, and it combines in the theory of everything. If we have only one theory at a larger scale, then we will have the theory of everything. Then it will decompose to these forces when we go to the lower energy scale. Okay, I will mention on the elementary particles in some detail. Maybe you will not see clearly but you can look at your paper and the PDF file also, which is online on the Indico page. Okay, these are bosons. Let me mention shortly. Bosons, force carriers, graviton, photon, gluon, weak gauge bosons, and the Higgs boson here. We will have some properties of them: mass, charge, spin, and strength, and the interaction range here. Matter particles, fermions, are grouped into three families: leptons and quarks. First family here, and then second family here, and then the third family here. The top quark has the highest mass in the fermion part. Okay. The forces are responsible for some physical events. For example, electromagnetic force. Electromagnetic force responsible for composing of atoms and the light, chemistry, and electronics are closely related to this interaction. Strong force is responsible for the strong interaction into hadrons of the quarks and gluons, and the weak force responsible for example beta decay, neutrino interaction, burning of the sun, and some other events. And the gravity, you know, for also planetary system and the big size objects. Okay. There will be some Feynman diagrams here, but I'm sorry for the it's not seen. Okay, force carriers here, and then we can go. In particle physics, there are symmetries and the conservation laws. Noether theorem says if there is an symmetry, then there will be a conservation law. For this reason, we may group some of them here. Symmetry, for example, if there is translation in time, it corresponds to the conservation of energy. If there is a translation in space, it corresponds to the conservation of momentum. Rotation to angular momentum, and gauge transformation makes charge conserved. Okay, what is symmetry and symmetry operation? If we want to study systematically the symmetries, then we need a group structure. Then an operation on this group. If Si and Sj are in the set, then the product is also in the set. This closure. There is also identity here, and the inverse stated in this one. Associativity here. If we change the order of the operation, it remains the same. For the function, if we set minus x by x, then this this function will remain the same. Here you see the symmetry of the triangle. In particle physics, how will we use some symmetries? Translations in space and time form an abelian group structure. What it means? Abelian means if we change the order of the operators, Si, Sj, Sj, Si, here we call the abelian group. But the rotations in 3D do not abelian in this case. If the elements depends on the continuous parameters, for example, angle of rotation, we can rotate at any angle. The group is called continuous. And if the elements are labeled by an index, I, j, k, for example, goes from 1 to some values, then we can call them discrete groups. I mentioned these properties because in particle physics, we group particles according to their symmetry principle, symmetry properties. The most common groups are of the UN type. U means unitary here. Unitarity is given here, but figure is not good. So they are n by n matrices. If unitary matrices have the determinant +1, they are called special unitary. So there is also another orthogonal matrices and special orthogonal matrices in the group. Okay, we start with the for example, wave function or spinor or spinor, and we can transform these according to some rules. Let's call it a unitary transformation here. Then physics will be invariant under this transformation, like the rotation of coordinate axis. If we conserve the probability normalization, then psi times psi, which is a notation with bra and cat, psi prime, this gives us u dagger times u is equal to 1, which means that u has to be unitary. Then if we want to calculate the expectation value of the Hamiltonian, because if we know the interaction Hamiltonian between the particles, then we can calculate this expectation value. Here, if we make at the same time the unitary transformation here, then it remains the same. Here, it suggests that HU is equal to UH. You remember it with the commutation relation of the H and U is equal to 0. Then what it means, if you consider U as the infinitesimal transformation, it's given by a complex number, say, or in exponential form, then we can expand it in the order of the epsilon. Epsilon, we can take the epsilon is small here. Then we can neglect some epsilon square cube and some term. If we put it here in this case, then we will get again the order of epsilon square term and then neglect this one. We want this to be equal to 1. So it means G is equal to G dagger. Here, it's the unitarity requirement. If it commutes with Hamiltonian, then it means that by the Orhan theorem, G is a conserved quantity. So here you see 1, and well, doing nothing is also a symmetry operation. There is also discrete symmetries in physics, and the most important one, charge conjugation, parity, and the time reversal. Let me mention first on the charge conjugation. Classical electrodynamics is invariant under C conjugation, because even the fields reverse the sign, but there is an extra charge factor. Therefore, the force remains the same. You can remember the Lorentz force, for example. Charge operation on the p state gives you an anti-p state. It has the plus minus eigenvalues. It means that this symmetry operates on some internal quantum numbers, such as charge, baryon number, lepton number, strangeness, etc. But it leaves unchanged some other properties like mass, energy, momentum, and spin. They will not change. But it has limited eigenstates. For example, photon, rho meson, eta meson, they are invariant under C conjugation. It is not a symmetry of the weak interactions, because charge conjugation is not a symmetry of the weak interactions, because we have no left-handed antineutrino. An extended transformation, instead, an extended transformation, G parity is used. G parity is C times R2, which is an exponential factor here, I times pi, and the second component of the isospin. In this case, all pions are eigenstates of G. But we cannot say this for the charge conjugation. Another one is the parity. Lee and Yang proposed an experiment in 1956, for testing the parity in weak interaction. And it is seen that in beta decay, the most of the electrons are emitted opposite to the nucleon spin. It showed that the parity is not conserved in the weak interactions, but they are still a good quantum number, good symmetry in electromagnetic and strong interaction. So some of the properties of this transformation. For example, for scalar, this is P S gives you S if S is scalar, and for pseudoscalar, it gives minus sign. For vector, it gives a minus V, and pseudo vector or axial vector, it gives A again, and it doesn't change sign. From this experiment, we also comment the neutrinos are left-handed and the antineutrinos are right-handed. For the time reversal, T, and the TCP theorem, this is very difficult to test time reversal symmetry, because it is difficult to change the arrow of the time. Maybe we can consider this process. For example, neutron plus proton goes to D plus G. G means gamma here. And we can reverse the order of this process. d plus g goes to n plus p, for example. And there is no evidence for the violation of the t in this case. But the most sensitive experimental tests are the upper limits on the electric dipole moments of neutron and electron, which are in the order of 10 to the minus 26 or 7. Then TCP theorem states that the combined operation of them, T, C, and P, time reversal, charge conjugation, and parity, is applied in any order, is an exact symmetry of any interaction. Okay, in particle physics, we group the particles in some symmetry rules. For example, U1, SU2, and SU3. Quarks are grouped according to the SU3 group and also to SU2 group. This gives us an electric charge. This is just a complex number here, which is the generator of the U1 group. There are 3 2x2 matrices as the generator of the SU2 group, and 8 3x3 matrices for the SU3 group. Here you see B, R, and G. These are the colors of the quarks, 3 colors, and then anti-colors. So quarks can form, quarks will form hadrons, and in hadrons there will be confinement because quarks are confined into the hadrons. They are not going out. If we look at these two pictures, for example, here you see electron and positron, for example, and these lines are the electric field lines. If we move them apart from each other, then the electric force fields will be spread out. Okay, and because the Coulomb force is proportional to the inverse square of the radius for length. In the quark case, for example, this forms a hadron, Q anti-Q, Q. If you have enough energy to separate them inside the hadrons, then if you separate them, for example, in this figure, then there will be a flux tube here, color flux tube, and the lines not will be separated. They are also become condensed way. So if we go, if we continue to separate them each other, then in this case there will be two pieces. They are also QQ bar and QQ bar states, which we call them as mesons. This shows us the quark, the fact that the quarks are confined into hadrons. Okay, hadrons means mesons and baryons. What are mesons? Mesons are grouped in some symmetry principle again. For example, if we label L for the angular momentum, orbital angular momentum, and then parity T minus 1 to the L plus 1. For QQ bar mesons, the charge conjugation will be C is equal to minus 1 to the L plus S. And the G parity gives here. According to the SU4 classification, we have the decomposition here, 15 flat plus a singlet here. And the spectrum will be given in this formula. Here you see the some replacement of the mesons. For example, D mesons here, pi mesons here, eta here, and there are also rho meson, J psi here in the middle. And if you look at this layer, on this layer, then there will be some quantum numbers here. For example, Q charge, plus 1 line here, 0 line here, and the minus 1 line here. And these are also the lines for the strangeness, because K mesons has strangeness plus 1, and the pi's have 0, and the K minus or anti-K 0 have the strangeness minus 1. What about the baryons? Baryons is a bound state of the 3 quarks, QQQ states, and because it is a fermion, then its wave function should be antisymmetric. Then we can label it antisymmetric. The color is also antisymmetric, which should be multiplied by another function consisting space, spin, and flavor. It should be symmetric here, because antisymmetric times the symmetric one gives you the antisymmetric state. It is useful to classify the baryons into bands having the same quantum number of excitation. Here you will see a pyramid-like shape, and here a triangle and some other hexagonal shape. In this case, you will have 3 main axes. One of them is the third component of the isospin. Another one is the strangeness, and the other one is the electric charge. According to these, we can group baryons into these figures. Okay. Symmetries in particle physics is an important ingredient, and now we will go to the gauge symmetry or phase transformation. Every force can be derived from the principle of internal symmetry, and the local gauge invariance predicts gauge bosons. That's why we have to understand what the gauge symmetry, gauge invariance is. So we can take a sphere in this figure. If we apply a global transformation, then we can rotate this sphere around this axis. Then we do the global transformation, which means that here e to the minus I q or theta, it should be theta. Theta is not dependent on the space. And here it's a local transformation in 3 dimensions, let's say. Maybe we can also show it in 2 dimensions. In a plane, we can make different rotations everywhere. Then we can make local transformation. local transformation is important, and the global transformation is also. In the previous slides, I have mentioned that the charge conservation comes from the global transformation, as you know. And what's the result of the local transformation, and which conserved quantities and conservation laws correspond to this symmetry? We will see later. Okay, let me go a bit different topic on the 4 vectors, because we want to make some calculations on 4-dimensional space-time. Then we want to use 4-vector notation. For example, covariant component of the momentum p mu is given by this relation, and the covariant contravariant component and the covariant component here. In particle physics, we deal with the relativistic particles, and we have to use 4 vectors. That's why, because we need some Lorentz invariants. Then this is an invariant mass, p mu times p mu is equal to mass square, which is valid also for the free particle. It's the phase of the wave function, x mu p mu, and the Lorentz transformation for the energy and the third component of the momentum is given here, cosine hyperbolic y0. Y0 is called here rapidity. This is just an example. You may study in the evening or later in the school times. Then if there is an unknown things and you cannot do some calculations, then you can ask me during the school. So I will pass this one and another one. Okay. In order to use the time, my time, so I need to mention on the interaction Lagrangians, which leads to the vertex factors. If we write down the QED interaction term in this form, it is given minus GE, Q, and psi bar, gamma mu, psi, and A mu. Here, the psi denotes the fermion field, and the gamma mu matrices, and the A mu denotes the vector field. There are 3 fields here, psi bar, psi, and A mu. Then it defines a vertex, fermion, antifermion, and the vector boson vertex. And the interaction coupling constant is given here, GE, and the charge is given as Q. So if we want the vertex factor from this interaction Lagrangian, then we can remove the fields and multiply the remaining terms by I. Then we will get the vertex factor here, minus I times GE, Q, and the gamma mu. This is gamma mu. So this is valid in QED, but in QCD it has a different vertex factor because of the structure of the generators. In this case, for example, we are in the U1 group, and in this case we have to do calculations in SU3 because quarks have color. this one or that one? Anyone. Okay. Okay. We may measure electric charge, and also we may measure, for example, decay width. If one particle decays into two, then it will be a triple vertex. Just in this Lagrangian, then if we measure the decay width, we will know that which is the relevant factors for this interaction. Okay. Here the gluon field G, psi is again the fermion field, and the lambda are the matrices, which is the generator of the SU3. We can measure charge decay width of a particle. Mass is not here. It will be come. It will come later slides. Is it okay, Jotan? Yes. If one particle decays to another, then we can measure the another particle. Then we can measure also the strength of the interaction. It means that we can do it. Interactions. We have three interactions in particle physics, which we can combine them in a single theory, for example, or single model. Let's just call standard model. Gauge bosons interact with the fermions as described by the vertices. Here there is a strong interaction vertex, and the coupling strength is given by GS here. Q quark and gluon vertex, muon, antimuon, and photon vertex. The coupling constant is given here E. E means electromagnetic coupling constant. And the weak interaction in two parts, charge current and the neutral current. It changed the flavor. D quark comes and U quark goes. So it changed the flavor. And the coupling constant GW, here the coupling constant GZ. In the strong interactions, flavor doesn't change. Q comes, Q goes. And in the electromagnetic interactions, muon comes and goes. No other particle. For example, muon comes and electron goes. No, there is no process in this level. Okay, this one Q D goes, D comes and U goes. Q comes and Q goes again. Also, this interaction doesn't change the flavor. Their strength is given here approximately at very low energies. For example, alpha S, if it is order of 1, then electromagnetic fine structure constant alpha 1 over 137, and the alpha WZ is the order of 1 over 40. So we have now interaction terms, and we want to calculate the amplitude for decay width calculations or cross-section calculations. Here you see J mu x, J mu y. These are the current dependent on the space x. Here you see E square over Q square in the middle and J mu. We can make a Fourier transform between them. In the phase space, this term, we will get this term in the phase space. And if you look at the elastic scattering, for example, looking from this side, one particle comes and it goes by interacting in the middle, a gauge boson. So we have free Lagrangian terms and interaction Lagrangian terms. We can derive the vertex factor from the interaction Lagrangian terms and the propagators from the free Lagrangian terms. So for spin 1, the propagator will be given in this form. For spin 1/2 will be given in this form, and for spin 1, this one, the interaction factors, interaction terms gives us the vertex factors for QED, QCD, electroweak interactions, and we can also draw the Feynman diagrams corresponding to a process or for a sub-process. What shows you an Feynman diagram? For example, this one. We have in the initial state, for example, this one, electron-positron annihilates by exchanging photon here in the middle, and we will get the final state here in time and in space, for example. So this diagram shows a penguin diagram, which is important in the meson decays. And this one is a QCD diagram. Green quark comes here, and anti-blue comes. Then the gluon exchanged here, gluon color, green and the anti-green. One quantum number from this quark and another one from this quark. So in the initial stage we have a color state. Then in the final state we also have the same color state. In this process, which is a neutral current weak process, electron-positron comes, annihilates, and the Z exchanged here, and the QQ bar produced. Here you see a gluon-gluon fusion. Gluon-gluon comes from the proton, because proton is a composite object. There are the partons inside it. We can call them quarks, gluons, antiquarks, but in high energies. If you go very low energies, then we will see only 3 quarks, UUD, for example. They are the valence quarks. They can form a bound state. Here, there is also a triangular loop, because here you see H, Higgs, gluon-gluon Higgs coupling will be in a loop, by loop. It's not in a point vertex. There will be form factor like things. Then it will decays to BB bar chords. Okay. We can complete the Lagrangian for the electroweak interaction. For example, this one for fermion fields. If we write the terms, for example, this one, this shows the psi bar, psi, and the Z, fermion, fermion, and Z interaction, Lagrangian, fermion, fermion, antifermion, fermion, and the photon interaction term. and this one fermion, antifermion, and the fermion, and the double boson interaction term. The first term gives us, we have here D slash means gamma mu times d mu. D mu is a derivative according to the x mu. Then it's the kinetic term for the fermion field. This the mass of the fermion. Then it will give us the mass term of the fermion. And there is here H, then Higgs. We have again three fields, psi bar, H, and psi. This gives you triple vertex. Then the fermion Higgs interaction term. This one. Okay. If you want to calculate amplitude and the cross section, for example, differential cross section like this, then for a certain process we have to draw Feynman diagrams. They may be 1, 2, 3, and some other things. S channel in this diagram, and you see the T channel in this diagram. Maybe there will be U channel like this diagram, but we have to add two of them to give the total amplitude, and we have to square the total to get the differential cross section here. So it's an example again. You may study this one in the evening. If we want to calculate the cross section, we need to know the differential cross section from, for example, Fermi's golden rule. This one is an phase space factor here, differential phase space factor, and this one is the matrix element square or amplitude square, and this one is the flux factor for the incoming particles. If we go to the center of mass frame, then it will be the center of mass momentum of the first particle, and then the energy. So it's useful to define the Mandelstam variables here for two processes. They are especially useful invariants because we want to express the cross section in terms of the invariant quantities like the Mandelstam variables. So for two-body cross section, the differential cross section is given by this formula. If you calculate m square and then put into this formula and then the center of mass momentum of the first particle here, then you will get the differential cross section. So integrating over the t Mandelstam variable, you will get the total cross section. So you can measure this one. There are many things that you have learned up to now. So, but all the calculations are not easy. Some of them is difficult because they contain some loops and some radiation. So at tree level, and if you know the vertices of the interaction, then you can calculate the matrix element and then other quantities. There are some tools to calculate these things in a quick and efficient way. For example, COMPEP, CalCap programs can be used for the particle decay and collision processes. which gives you an automatization, high-level automatization for calculation of the cross-section, decay width, and even the event information. Okay, there is also an example you may study later. It gives you the kinematic distribution and the pair production at colliders. For example, this is a famous one, then I want to mention it. It's the TT bar production at hadron colliders. So Q comes here and the Q bar annihilates by exchanging gluon here and TT bar production. Then they decays into W and the B bar quark. This T decays into W plus and B, and the W again decays into U and D bar quark. There will be some other quarks in the final state also here, but at the elementary level we call them quarks, but in hadron level they will be hadrons and jets. So they become hadronized. Then the detector sees hadrons, not the quarks. Therefore, we have to know all the story from the beginning here, which is an elementary process. Here, gluon-gluon fusion by exchanging gluon and TT bar production. The same story here, and the picture of this process. Okay. Sorry. Yes. Okay. This is the maybe this is an easy one, because if we have, for example, 6 jet in the final state, because 2 comes here, 2 comes here, and if 2 comes here, then we will get 6 jets in the final state. It means that there will be some other background processes. Maybe in the final state, if we have a lepton, charged lepton, then we can use a trigger, and then we can define this one. Yes, in the jet case, there will be some backgrounds for this process, and it's the chosen one. Of course, they can decay into quark antiquark, and it's the probability is also, for example, W decays into 2 jets with a probability 70%, and this one is 10%. Then the 6 jet is the most probable one, but it's not chosen in some analysis because of the background analysis. Okay. then the cross section will be lowered by the not mostly probable channel, because it's 10% for the leptonic channel and the 70% for the hadronic. That's why if we want large event samples in the final state, then we can choose the most probable one first. And if it is difficult to analyze, then we can choose one of them is decay leptonically, for example. Yes, per lepton, yes. Another one. We can multiply 3 for, but the tau decays to hadrons, then it becomes difficult again. So, okay. So what about the missing transverse energy? Yes, I should mention on this, because in the hadronic events like this, there will be some missing part, because neutrinos are not detected by detectors and they carry energy. So an important portion of the incoming hadron energy goes into the beam pipe in this direction. So for some particles which are not detectable by detectors, will carry transverse energy, transverse momentum, then we can measure this one. In this formula, you will get a summation over the PT of the all measurable particles in the final state. If you know, if we measure the PTs of the particles in the final state, then we can add them and then measure the missing transverse energy. It is not possible to measure the longitudinal part of this one because of some unknowns. Okay. For particle decays, the similar formulation, like as in the cross-section calculations, we will have again here phase space. In the initial state, we have one particle, and in the final state, we will have more particles. Goes to Pn, and this is the factor for the decay width calculation, differential decay width, and the phase space is given here, which tell us the momentum for momentum conservation in this relation, and the MFI is the initial to final state transition amplitude. Okay, I will come to the standard model. Then I think I have some few minutes. The gauge group of the standard model is SU3 times SU2 times U1. The indices here, color for C for color, W for weak, and the Y for hypercharge. And there are 8 Coulomb fields here, and 3 fields for the weak interaction and the B mu. We can define the mass eigenstates in a unified theory. So we will have the third component of the W's and the B as the photon and the Z boson in a different combination. For example, W plus and W minus, for example, these are the mass eigenstates for the W and the W plus and minus bosons. Then we can define them in terms of W1 and the W2. So it's an picture. for the particles grouped here, elementary particles grouped according to their structure. For example, upper quarks UCT, which has charge 2/3, and the down quarks which have minus 1/3 charge. So gluon, photon, and Z and W bosons, force carriers here, and the first two, second, and the third families. Okay. The another part of the standard model is the electroweak symmetry breaking. In the electroweak symmetry breaking, gauge bosons and the fermions get their masses from a vacuum expectation value of the scalar field. So we need a scalar boson Higgs here, and the vacuum expectation value 246 GeV. I will mention it great detail. For example, field theories will be mentioned in some other lectures. Then I will come to this slide. What's the result of the global and phase transformation in the standard model? Then we can look at the free Dirac Lagrangian like this Lagrangian. So we can apply global phase transformation, and which is invariant under this transformation. It gives us the charge conservation. For local phase transformation, there is an extra term like this, because the phase factor here, the transformation here contains x dependent. Then if we derive it according to x, then there will be extra term, because in the global case there is no x dependence. So we have to compensate this term with that one, and this gives us the total Lagrangian should remain invariant under the local phase transformation, and this will give us free Lagrangian of the gauge field, and interaction Lagrangian, and also the this term. But this term has a special meaning. I will mention it later. For the U1 gauge symmetry, we will have the electromagnetic quantum the Lagrangian for the QED. For example, this first term is the kinetic term, fermion part. This one is the interaction term, and this one is the mass term, and this one is the vector boson kinetic term. We can transform it by using, for example, psi to psi prime, and then global or local changes. Then it should remain invariant under both global transformation and the local transformation. Okay, the Young-Mills extended this symmetry, the local symmetry, to non-abelian case, and transformation matrix S is given here, which contains the generators of the group tau times lambda, for example. Then we will have 3 components of lambda and the 3 matrices for tau. So covariant derivative in this case can be read as this one, the extra term here, and then scalar product transformation here. Then we will have the Lagrangian, which is invariant under local SU2 gauge transformation. Okay. Here you see the kinetic term for the fermion field, mass term, and the kinetic term for the vector fields, and the interaction term. If we expand this term, tau has three components, and the A also three components. Then we can combine them in a suitable way to get W boson, W plus minus, and Z, and also photon. Okay. Electroweak symmetry is broken. How this happens? What does it mean? We will learn the details of this one. Some symmetries are not exact. They are broken, and this is very important for the particle physics also. Spontaneous of the symmetry predicts the masses for the fermions and the gauge bosons, massive gauge bosons. Not for photon and then not for gluon, because they are massless. And predict one more massive particle, the Higgs boson, which is responsible for the mass generation, and the only missing and most wanted part of the standard model. Spontaneous symmetry breaking. Here you see a Lagrangian, scalar Lagrangian here, and which has a symmetry. If we put phi to minus phi, then it will become invariant. So there are two minimums in this potential. If we move to one of them by transforming this field, so it's a new variable, and the converted Lagrangian is given here. If you put eta to minus eta here, then there is an eta cube term here, and then this Lagrangian will not be invariant under this transformation. Then we say the symmetry is spontaneously broken. So in the Higgs mechanism, there is a complex field phi here, defined here, and the Lagrangian in this form. Before the spontaneous symmetry breaking, we will have three fields, for example, phi 1, phi 2, and A. After symmetry breaking, they will change according to this one. Due to the choice, phi 1 prime phi 1 and the phi 2 prime is shifted with this one. So the massless Goldstone boson will be disappeared, and give degrees of freedom to the vector bosons. So the vector bosons will be massive, and also the Higgs boson has a mass in this mechanism. So it's important ingredient of the standard model. Gauge boson get their masses from the scalar kinetic term shown here, and finally we will have MW and the MZ in terms of the vacuum expectation value. Fermion masses are from the Yukawa couplings written here, Yukawa interaction terms. There is a vacuum expectation value and the Higgs field here. It gives also the interaction between the Higgs and the fermion fields. About the neutrinos, because the leptonic sector of the standard model should be well tested and understood both in mixing and the neutrino masses because they are important. For this case, neutrino mixing in this way, for example, considering only atmospheric neutrinos, nu mu and nu tau case, there will be a mixture of them, nu 2 and nu 3. And they will have an time dependency in the exponential form. So what about the neutrino masses? Neutrino masses is a difficult ingredient of the standard model because we have only the left-handed neutrinos. With this mechanism, it is not easy to give masses to neutrinos. If there is a right-handed part for the neutrino, then we can write a term like the quarks or the or the charged leptons, but it is not easy. In this case, we may define neutrinos have both Dirac mass and the Majorana mass. Then we can combine them in a suitable way, leaving one of them is very light and the other one is very heavy. This is just the seesaw mechanism mostly used in the grand unified scale. So the standard model has some parameters, 3 gauge couplings, 2 Higgs parameters, 6 quark masses, 3 quark mixing angle, and 1 phase, 3 lepton masses, and in the mixing case there is also another parameters. So there are many parameters in the standard model, but not too much when compared to the other theories. There is also flavor problem which should be solved. Some of them is some of the particles are have high mass, and the other one has very small mass, and it makes a mass hierarchy. So the flavor physics deals with these 2 quarks, P quarks and the C quarks and the E quarks. And the CP violation in the standard model comes from the CKM matrix, which originates from this matrix. But in the leptonic sector, it is not easy to say something, but it can be formulated in the same way. The well-known triangle unitarity from the electroweak data and low energy data, and also from the low energy data, the phase, the measured phase factor is very small, in the standard model for the because it is responsible for the CPU violation. And the parameters are given here, which can be found in the PDG. Okay, there is also baryon asymmetry in the universe, and it can be calculated with the assumption only one parameter in the CKM. In this case, the order of the asymmetry is not matched. The calculated one and the measured one is not matched. So it should be some sources of the CPU violation. In the new physics theories, maybe there will be some suggestion for this discrepancy. Okay, that's all for my first lecture. If there is a question, then I will answer. Okay. Any question? Yes, please. Yes. Maybe we can consider Coulomb force law, for example. If we have two charges, then they will interact each other, right? Yeah. Okay.
But the thing is, for two charges in F,
Yes. Yes.
K is some sort of
Coupling constant. Maybe we can consider it in the natural units, for example, not in the SI units, because we can choose the K constant in some unit system differently, because in the natural units we take H bar and C is equal to 1. Then their units become different. Yes. Maybe it is easy to consider from the equation of motion. For example, if you know Lagrangian, then we can get the equation of motion by using Euler-Lagrange equation, for example. In the Lagrangian, there is a coupling constant for the triple fields, right? Okay, it can be converted to the force, and then we can comment on the K constant in terms of the G constant in the Lagrangian, for example, right? Yeah. Okay, another question, comments? Yes. Okay. You have a coffee break right now?
Şeyler